The goal of this video is to derive the velocity and acceleration from a position versus time graph. Here we have a plot with position on the y-axis and time on the x-axis. We can sketch in a position function that looks like this, where x of t is equal to negative t squared plus 4t. Velocity is defined as a change in position over a change in time, that is, displacement over a time interval. The bar here indicates that we are actually referring to an average velocity over a relatively large time interval. If we choose any 2 points on this graph, we can determine the average velocity over that interval. For example, take the points at the beginning and middle of our function. The final position over this interval is 4 meters, the initial position is 0 meters. The final time is 2 seconds, the initial time is 0. This gives me an average velocity of 2 meters per second, which is the slope of this green line which connects the 2 points. The interval over the second half of the function will give us negative 2 meters per second. Sketching this average velocity over a time interval will look like this. The velocity function is just the slope of the position function, which I've approximated with the green lines. But notice that this really only gives a vague idea of what's happening. To get more information out of the velocity versus time plot, I'll need to use a smaller time interval. Let's try the interval that occurs over 1 second. The slope of the line connecting the points is 3 meters per second. The next interval has a slope of 1 meter per second, then negative 1 meter per second, and finally negative 3 meters per second. Plotting all 4 of these intervals on a velocity versus time graph will look like this. Notice how our approximation of the position curve has increased dramatically. If I again double the number of intervals being used, I'll get an even better approximation of the position as a function of time, and even more information out of the velocity plot. Again, each of these velocities represents the slope of each green line on the position plot. Looking at the velocity intervals more closely, you should begin to see a pattern forming. The more intervals I use, the more information I'm getting. This increase in information comes from how closely our approximation fits the actual position function. As I decrease the time intervals, the approximation gets closer and closer to the actual function. If you imagine extending this until the time interval is nearly 0, you'll see that our approximation approaches the actual position function. Mathematically, we are taking the limit of our average velocity as the time interval approaches 0, which is the definition of a derivative with respect to time. Take a large time interval beginning at t equals 1 second. The slope of the line connecting the points represents the velocity of the object. Over a 2-second time interval, the slope is 0, even though the object itself has a non-zero velocity. As I decrease this time interval, the slope of the line approaches the slope of the function at t equals 1 second, until eventually the green line will intersect the function at only t equals 1 second, at which time I've found the instantaneous velocity of the object at t equals 1 second by finding the slope of the tangent line there. The instantaneous velocity is the slope of the tangent line at a given time. If I found the tangent lines at every point on the position function, I would be able to plot the instantaneous velocity as a function of time. It is easy to find the equation that generates a line like this by looking at the slope and y-intercept. This plot fits our pattern very well. Compare the position and velocity plots over the same time interval to help get a feel for the relationship between the two. When the velocity is equal to 0, the object is temporarily at rest. Its position does not change, indicating it is at a maximum or minimum value. When both the velocity and the position are positive, the object is getting farther away from the origin. As the velocity approaches 0, the object gets slower and slower until it comes to a stop at t equals 2 seconds. Then, with a small negative velocity, the object is slowly moving back towards the origin. As the velocity gets larger, the object is more quickly returning to the origin. If I measured the position beneath the time axis instead, the same relationship holds. When the position and velocity have the same sign, the object is moving away from the origin. When the position and velocity have opposite signs, the object is moving back toward the origin. From the velocity function, I can repeat the procedure to determine what the acceleration must be. Average acceleration is a change in velocity over some large time interval. Instantaneous acceleration is the limit of the average acceleration as that time interval approaches 0. Notice that for any time interval I pick here, the slope of the velocity function is always the same. The tangent line is the same everywhere. the average acceleration is the same as the instantaneous acceleration everywhere. Everywhere, the acceleration is a value of -2. Plotting this will simply yield a horizontal line at a equals -2 meters per second per second.